Hi everyone. So last time we looked at improper integrals with infinite domains, and we saw that if the domain was infinite, we need to take appropriate limits in order for that to make sense. So now we're going to look at the second case of improper integrals, and that is with discontinuous functions. Yeah, more specifically, functions with vertical asymptotes. So let's say we have a function with an asymptote like this. Okay, so we've got x and y, we've got some function, but it's got a vertical asymptote at b. Okay, and we want to find the integral from a to b. So we want to see what is this area here. Okay, now we can't directly do this because we see that on the right-hand side of the area, we have a vertical asymptote. Okay, so we can't integrate directly up to b because there's an asymptote there. So instead, we find the integral as a limit approaching b. So the integral from a to b of f of x dx. Okay, we can't do that directly. So instead, we take the limit as t approaches b minus. So we're approaching it from the left-hand side. Then we take the integral from a to t, f of x dx. So this t is somewhere here. And then we take the limit as t approaches b. So we get closer and closer to this asymptote. Now, if this limit converges, then we say that our original integral here also converges. If the limit diverges, then the integral also diverges. Okay, so this is what we mean by integrating up to an asymptote. Now here, the asymptote was on the right-hand side of our area. We could also have the case where the asymptote is on the other side. So let's look at that. So let's say we've got an asymptote here, and then our function does something like that. So here's our function f. Okay, and we want to go from a to b, where a is an asymptote. So we want to find this area here. Now, again, we can't just substitute this value a because the function is infinite there. So instead, we take the limit as t approaches a. So the integral from a to b, f of x dx. Okay, we can't substitute a directly because the function's infinite. So instead, we take the limit as t approaches a plus. Okay, because we're going from the right-hand side now. And then we take the integral from t to b, f of x dx. Okay, so depending on which side of the asymptote you're working with, you will then take the appropriate limit. Okay, either the limit from the right or the limit from the left. Now, what happens if the asymptote is in the middle of our area? So maybe we have something like this, where we've got our function, and it does something like that. Okay, let's say there's an asymptote at c. So now we're trying to go from a to b with an asymptote in the middle of our area. Okay, so we still want to find this area here. Okay, but there's an asymptote in the middle, so we need to take care of that. So the way that we do this is to split this integral into two parts. We find the integral on the left-hand side of the asymptote and add it to the integral on the right-hand side of the asymptote. So if we're integrating from a to b, f of x dx, then we deal with the left-hand side. So that will be the integral from a to c, f of x dx. plus the integral from c to b f of x dx. Now we know how to handle these two. We need to use the appropriate limits. So this is going to be the limit as t approaches c minus, because we're on the left-hand side, the integral from a to t f of x dx, plus, and now for the other side, the asymptote is on the left-hand side. So this is going to be the limit as t approaches c plus, okay, because we're going from right to left, the integral from t to b f of x dx. So you see that if the asymptote is in the middle of our area, something like this, then we split it up into two parts. We do the integral for the left-hand side of the asymptote, taking the appropriate limit, and we do the integral on the right-hand side of the asymptote, again, taking the appropriate limits. So in all three cases, we need to take the limit as we approach the asymptote. We can't directly substitute. Okay, because if we did directly substitute, the function would just be infinite. We wouldn't get a reasonable answer. Okay, are there any questions about this process before we look at some examples? Okay, let me just look in the chat. No, okay. Okay, yeah, so remember, if you've just joined now, please put your student number in the chat, just so we can take it for attendance. Okay, any questions before we look at the examples? Yes, on the second rule. Okay, yeah, what's your question? Yeah, do you have a question to ask? Okay, let's take a look at the examples. Okay, example 1. Okay, I've got a question here. Do we start from the asymptote to the function, from c to a and b to c? So here, let's go back here. For this case here, if we have an asymptote in the middle, then we're going to split this up into two parts. So part 1 and part 2. For this first part, it's the integral from a to c, f of x dx. And then for the second part, it's the integral from c to b, f of x dx. But here we need to take the limits. So since c is our asymptote, we need to take the limit as t goes to c minus for the first part, and then t going to c plus for the second part. So we can think of that as, on the left-hand side, we're approaching c like that, okay, from the smaller values of x going across. And then for the other one, we're starting here and we're approaching it from the right-hand side. So it's something like that. Okay, so those are the two limits that we're taking. Okay, let's have a look at the examples. Sorry. Okay, so the first example, we have the integral from 2 to 5, 1 over the square root of x minus 2 dx. Okay, something like that. Now, we know that this function is discontinuous at x equals 2, okay, because the denominator is 0. So the function goes to infinity when x is equal to 2. Okay, because the denominator becomes 0 in that case. So we need to find this integral in terms of the limit. So we're going to take the limit as t goes to 2 from the positive side, because the asymptote is going to be on the left of the area. The integral from t to 5. And then we can rewrite this as x minus 2 to the minus 1/2 dx. Okay, so since the asymptote is on the left-hand side of our area, then the limit is going to be t approaches 2 plus, okay, because we're going from the right. Okay, so now this is just a standard integral to do. Okay, just ignore the limit for now. We do this definite integral, and then we take the limit. Okay, so let's do that. So this is going to be the limit as t approaches 2 plus. We do the integral. That's going to be, we add 1 to the exponent to make it half, divide by that. So that's going to be 2 root x minus 2, evaluated between t and 5. Okay, so now we do the evaluation. So this is going to be the limit as t approaches 2 plus of, we're going to have 2 root 3, because if we substitute 5, we're going to get 5 minus 2, that's 3, minus 2 root t minus 2. Okay, so we need to take this limit now. Now, the first term here is a constant, so the limit doesn't care about that. So this is going to be, this is going to be 2 root 3 minus 2 times the limit as t approaches 2 plus of the square root of t minus 2. Now, this expression over here is continuous. So we can substitute t equals 2. Okay, remember, if the function is continuous, you can just substitute the value of t. So if we substitute that, we're going to get 2 minus 2, which is 0. So in this case, our final answer is just 2 root 3. Okay, because that second part goes away. Okay. Any questions about this example?
Yes, sir.
Yeah.
Can you please tell me how can we see that the asymptote is on the left?
Oh, because we can just draw a picture of that. So we're going from 2 to 5, and the asymptote is at 2. So we're working on this side from 2 to 5, and then the asymptote is at 2. Okay, so it's on the left-hand side of our domain here. Okay, any other?
Thank you.
Okay, any other questions? Okay, let's take a look at the next example then. Okay, example 2. So here we're trying to find the integral from 0 to pi over 2 of sec x dx. Okay, so now we need to check if there's any asymptotes here. So remember that sec x is 1 over cos. Okay. When x is equal to 0, cos of 0 becomes 1. When x is pi over 2, cos pi over 2 is 0. And that's a problem for us. Okay, because we are going to be dividing by 0 in that case. So that means pi over 2 is an asymptote. Oh, someone's saying my screen's frozen. Is it still frozen? Can you see me writing? Okay, let me just try. Okay, so everything's back. Okay, let me just try reshare here and then we can go. Okay, so pi over 2 is an asymptote. Okay, so from 0 to pi over 2, everything's fine, but at pi over 2, this function goes to infinity, which means we need to take the limit as we approach pi over 2. It's not back. Okay, let's stop sharing. Okay, let's try redo that. Okay, how's that now? Okay, awesome. Okay, so pi over 2 is our asymptote in this case. So we need to take the limit as we approach pi over 2. So this integral is replaced with the limit as t approaches pi over 2 minus, because we're going from the left-hand side here. Then it's going to be the integral from 0 to t sec x dx. Okay, so we need to evaluate the integral with t, and then after that, we take the limit as t goes to pi over 2. Okay, so this is going to be the limit as t approaches pi over 2. Now, the integral of sec, we've done that quite a few times now. That's going to be the natural log of sec x plus tan x. Okay, it's just something you need to remember. And then this is going from 0 to t. Okay, so again, we leave the limit alone for now. We substitute t and we substitute 0 to get a function of t. So this is going to be the limit as t goes to pi over 2 minus. If we substitute t, we're going to get the natural log of sec t plus tan t minus the natural log of sec 0 plus tan 0. Okay, now remember how sec is defined. Sec is 1 over cos. So if we substitute 0, we're just going to get 1. So this is just going to be 1. And tan of 0, that's 0. So that's going to be 0. Lastly, the natural log of 1 is 0. So all of this goes away. Okay, so we're just left with the terms involving t. So this is going to be the limit as t goes to pi over 2 minus the natural log of sec t plus tan t. Okay, so let's see what happens here. Now, sec, okay, as t approaches pi over 2, what do we get? Well, we know that sec going to pi over 2 goes to infinity. because we're dividing by 0 in that case. So for the first part, we can just say that that's going to infinity. And what about tan? We know that tan of pi over 2 is also infinity. So the second term is also going to infinity. So we've got infinity plus infinity, that's just going to be infinity. So altogether, the limit also goes to infinity. In other words, it diverges. Okay, so there's no value to this integral. It just goes off to infinity. Okay, any questions on this one? Okay, so it's not too bad. You just do the integral as normal, and then your very last step is just evaluating the limit. If the limit goes to infinity, then you just say that it diverges. If the limit gives a finite number, then that's what your area is going to be. Okay, let's take a look at another example. Got a question here. Why did you change the x value for the bounds? Where is that? Where did I change the bounds? Sorry, why did I say cos? Oh, I'm not changing the bounds. That's just how sec is defined. So this was just a little side note. So it's just like a remember how sec is defined. It's not part of the calculation. So this whole part here, that's just separate. Okay, that's just a reminder there. Okay, so let's take a look at example 3. Someone's asking here how to see if there's an asymptote over here. That's what I was showing in this yellow cloud here. If we draw sec, so this is x, this is sec x, we see that it looks like this. So here's 0 and here's pi over 2. So there's a vertical asymptote here. Vertical asymptote because cos of pi over 2 is 0. So sec of pi over 2 will be 1 over 0, but that goes to infinity. Okay, so you just need to know that cos goes to 0 at pi over 2, which means sec goes to infinity. Okay, so this is how we know if there's an asymptote. Okay, so you just need to check, does the function go to infinity or not? If it does go to infinity, then we've got an asymptote there. Okay, no problem. Okay, let's go back to our third example here. Okay, example 3, we have the integral from 0 to 3 of 1 over x minus 1 dx. Okay, so just by looking at this, we see we've got a problem. So let's just write here. The denominator is 0 when x equals 1. So we have an asymptote at x equals 1. Okay, so if we look at our domain here, here's 0, here's 3. when x equals 1, we have a vertical asymptote. Okay, so if we want to find the integral, we need to split it up into two parts. We need to do this first part from 0 to 1. So let's call that part 1. Then we need to do the second part from 1 to 3. Okay, because we've got an asymptote in the middle of our domain. So the integral from 0 to 3, 1 over x minus 1 dx. We need to split it up. So it will be the integral from 0 to 1, 1 over x minus 1 dx, plus the integral from 1 to 3, 1 over x minus 1 dx. Okay, because we've got this asymptote here at 1. Okay, so we've got integral number 1 to do and integral number 2 to do. So let's start off with number 1. So for 1, this is going to be the limit as t approaches 1 minus, okay, because we're on the right-hand side here. Then it will be the integral from 0 to t, 1 over x minus 1 dx. Okay, so we can do this integral. This is the limit as t approaches 1 minus. This is going to be the natural log of x minus 1 from 0 to t. Okay, so now we want to substitute t and then substitute 0. So this is going to be the limit as t approaches 1 minus. If we substitute t, we're going to get the natural log of t minus 1. And if we substitute 0, it's going to be minus the natural log absolute value of minus 1. Okay, so this is going to be the limit as t approaches 1 minus. We're going to have the natural log of t minus 1 minus, and then the natural log of 1 is just 0, so that goes away. Okay, so now we need to take the limit. However, if I substitute 1, we see that we get the natural log of 0. But if we just look back at what our graph looks like, the natural log, at 0, this goes down to minus infinity. Okay, so as we get closer and closer to 0, the natural log goes further and further down to minus infinity. So this limit actually goes to minus infinity. In other words, it diverges. Okay, so remember what I said last time, we need both parts to converge for the integral to converge. Here we see that part 1 diverges, so we don't even need to calculate part 2. The whole integral already diverges. So since part 1 diverges, the whole integral diverges. Okay, so the integral from 0 to 3, 1 over x minus 1 dx diverges. Okay. Okay, any questions about this one? Okay, so that's enough examples for now. Later on, I will upload this lecture and also the pre-recorded lecture with a few more examples just to go through. Okay, but if you understand this now, then you should be fine. Okay, let's just end off with some homework problems for you to try. Okay, so just one homework problem for today. We have the integral from 0 to 1, the natural log of x dx. Okay, so just that problem for today. So the question, does it converge or diverge? If it does converge, what is its value? Okay, so just one problem for today. And as always, I will upload the solution later this evening. So you've got the rest of the day to go through the problem and then see what the solution is later on. Okay, and then as always, these bonus marks here, they'll go towards the remaining assessments. So we've got that summative quiz coming up and then test 3. So all the bonus marks that you've been collecting now, they will be split up between those things. Okay. So any questions about what we've done today? Okay, so next week, Monday and Tuesday, we will carry on with improper integrals. We've got a few more things to go through, like the comparison test for improper integrals. So we use that in cases where we can't directly integrate. So instead, we compare it to another integral. Okay, that makes things a bit easier when we are testing for convergence. And then after that, we have to do a small section on finding the length of a curve. Okay, so if I give you some curve, how do you calculate the length with an integral? And then that's it for the semester. Then you write your test 3. And then for those that qualify for the supplementary, that will come later. And then there's a couple that still need to write the catch-up quizzes. Okay, that will also happen later. Okay, but we should be focused on the summative quiz coming up next week. And then the week after that, test 3. Okay, and then the Monday and Tuesday before test 3, we will have a revision session for test 3. Okay, so if you have any questions, you can come to those lectures. Okay, but look out for these 2 lectures that will be posted later today. So this one and then another one on some more examples. Okay, I'll see you next time. Okay, bye everyone.